Hello friends, Namaste and Jai Hind. Welcome to my show Engineering and Technology Made Simple. In this session of mathematical models, today we'll see a very important model called matrix. Basically, a matrix is a collection of numbers represented in a rectangular grid as shown below inside the square brackets. What is the notion of representing group of numbers in a rectangular grid? The idea is we apply conventional algebra to single numbers. So here the question is it possible to apply rules of conventional algebra, that is addition, subtraction, multiplication and division, and the properties of this conventional algebra to a group of numbers represented in rectangular grid, which is considered as a single number? And the answer is yes. And hence the entire subject is evolved out of it, which is called linear algebra. So now we'll see what is a reason behind existence of such a matrix representation of numbers. So consider a simple equation y is equal to ax. Now this represents a system with input as x, output as a y, and system parameter as a, where a operates on x, which generates output y. Now if you want to solve this equation for x, then the solution is x equal to y by a, or a inverse into y, or y into a inverse. So here we could interchange the position of variables y and a inverse and still answer remain same. Now consider a simultaneous equation with two variables x1 and x2 as input variables and y1 and y2 as output variables with the system parameters a11, a12, a21 and a22. Now this equation can be solved for any parameter, that is for output if a and x is given, or input when y and a is given. So this can be done with the help of method of substitution, that is substitute equation for x1 or x2 from second equation into first equation and solve it. However, there is an elegant method to solve such type of problems. Now in this method, we segregate these three parameters as vector and matrices, where we already defined the matrix. So here there is an input vector with two variables x1 and x2. There is output vector with two variables y1 and y2. There is a parameter matrix having four parameters arranged in 2 by 2 format. Now this equation can be represented in a matrix form as shown below, that is a boldface letter y is equal to ax. Now before we see the solution, we'll see one more important point. If you want to switch from matrix equation to simultaneous equations for y1 and y2, how do you do that? And therefore there is a one rule evolved in matrix multiplication, and this is a foundation for the same. Now here we can obtain simultaneous equation for y1 by multiplying first row of parameter matrix, that is a11 and a12, with a column vector. So the rule is row of a matrix is multiplied with a column of a vector, and the same rule is applied whenever two matrices are multiplied as well. Similarly, we can find out equation for y2 by multiplying second row of parameter matrix with a column vector x1 and x2. So this is a basically point-to-point multiplication. So here we establish the rule of this new algebra, which is called linear algebra. Now coming back to the matrix equation, y is equal to ax. Now can we find a solution for x? And the answer is yes. We can apply similar rule as conventional algebra which we saw in a single variable equation. Now here we'll assume A inverse exists. So whenever A inverse is multiplied with A, the solution is 1, or in linear algebra it is called identity matrix. So the meaning of identity matrix is whenever it is multiplied with a vector or a matrix, it generates the same result. So here in this equation, I multiplied with x, it is the same as x. Then the solution for x is given by x equal to A inverse into y. Here we made one assumption that A inverse exists. Now what is a formulation for A inverse? It is already given in textbook as A inverse is equal to adjoint of A divided by determinant of A. In this short lecture, we are not going to discuss in detail the adjoint of A and determinant of A. We'll make an assumption audience already know these two operations, or if they don't know, they can refer some standard book for this operation. Our focus in this lecture is on the concept, physical interpretation and application of matrices. Now consider another important operation on a matrix which is called a transpose, which is obtained by exchanging rows with columns. This is a typically used in many operations to solve engineering problems. Now we'll see one exclusive case where the matrix is not a rectangular matrix. Now here A is a 2 by 3 matrix. So when you compute A transpose, you'll get 3 by 2 matrix by exchanging rows and columns. Now when you multiply A transpose with A, you'll get a 3 by 3 matrix, and the multiplication rule is same. Multiply row of first matrix with a column of second matrix. Similarly, when you multiply A with A transpose, you'll get 2 by 2 matrix. Now here, how one can compute the dimension of resultant matrix? The dimension of resultant matrix is row of first matrix multiplied with a column of second matrix. And therefore here you can observe one phenomena. When you change the order of operation, the final results are not same, and hence the new rule is evolved. It's called matrix operation does not satisfy commutative law. That is a change of variables position. Now why we are talking about a square matrix? The answer is very simple. The inverse of a matrix exists only when matrix is a square. That is a determinant of matrix is computed only for square matrix, and therefore inverse exists only for square matrix. Now here there is a one more important point to be noted is determinant of matrix A should not be 0, otherwise A inverse will become infinity, or one can say A inverse doesn't exist. What are the rules for a determinant of a matrix should not be a 0, which is also called a non-singular matrix? Now there are a couple of rules, we'll see one by one. Whenever any row or a column of a matrix is 0, then determinant will become 0. The second rule is if any two rows or any two columns are same, then still determinant become 0. Now the third rule is if any row is expressed as a linear combination of other rows, or any column, if it is expressed as linear combination of remaining columns, then it is called linear dependency. Then still the determinant of a matrix becomes 0. So one has to remember these three rules whenever you are computing inverse of a matrix. Now why do we need inverse of a matrix? to solve system design problems. There is a huge research is going on in computing inverse of a matrix, and the formulation given here, adjoint of A divided by determinant of A, is a highly complex operation, and sometimes it becomes practically infeasible or it is not a viable solution, and therefore different methodologies are invented or researched so that computation of matrix inverse becomes practically feasible. Now consider here one more point. Suppose matrix is not square, then is it possible to solve system design problem? So answer is yes. Now when you will occur across a non-square matrix, now in this simultaneous equation, if you assume number of equations are more than number of variables, or number of variables are more than number of equations, then you will come across system parameter matrix A, which is a non-square matrix. Now in this case, previously we saw a square matrix and therefore inverse exists. Such a system is called perfect system. But in non-perfect system where parameter matrix is not a square matrix, how one can find out the solution for X? Now here there is a simple technique one can apply, that is convert a non-square matrix into a square matrix. And we already saw the operation. When you multiply a matrix with A transpose on the left hand side or on the right hand side, you can convert into a square matrix. Now in this case, we'll multiply A transpose on the left hand side, and then we can compute inverse of a matrix. Now here A transpose A is a square matrix, and now inverse of A transpose A exists. So multiplying again both sides by inverse of A transpose A, which will convert the right hand side term into an identity matrix multiplied with X, and the solution for X is given as A transpose A whole inverse multiplied by A transpose into Y. So here we came across a new inverse definition of a matrix, which is A inverse is equal to A transpose A whole inverse into A transpose. So this is not a conventional inverse operation, and hence it is called pseudo inverse of a matrix, which is defined for non-square matrix. Now here we saw the simple operation to solve the system design problem or system solution problem with the help of matrix definition. Now what is a physical interpretation for a matrix? A matrix you can visualize as system parameters. A matrix one can visualize an operator operating on a vector. A matrix one can visualize an operator operating on another matrix where the multiplication rule is defined as row of first matrix is multiplied with a column of a vector or column of another matrix. So because of simultaneous equation representation, this rule is evolved in the multiplication process of matrix. Now here we'll see some important properties of matrix which will simplify the operation of computing matrix inverse, because as I had already mentioned, the conventional formulation adjoint of A divided by determinant of A is practically not feasible in majority cases. So now what are the various properties one should learn so that computation of matrix inverse becomes simple? So first property is a symmetric matrix. Now here a symmetric matrix is defined as A equal to A star, where A star operation is nothing but transpose of A and then apply conjugate of all the members of A. All of you know the conjugate operation in which sign of A imaginary part of complex number is reverse. If matrix is a real, then A star is same as A transpose. So this is a simple operation one has to understand whenever dealing with a real matrix or a complex matrix. Now, another very, very important property in matrix is called orthogonal matrix. Now, what is the significance of orthogonal matrix? A inverse is a trivial, and that is the simplest solution to compute A inverse, which is given by the following equation: A inverse is equal to A star. Now, A star is a transpose conjugate of a matrix A, assuming matrix is complex value. If it is a real, then A inverse is equal to A transpose. Now, what is our concept of orthogonality? Or when one can say the matrix is orthogonal? If dot product of any two rows or any two columns of a matrix is 0, the matrix is called orthogonal matrix. Now, what is an orthonormal matrix? Orthonormal matrix is same as orthogonal matrix. Only the difference is the magnitude of any row or any column is equal to 1. Otherwise, there is no difference. Now, third one is unitary matrix. It is also an orthogonal matrix, but the concept is extended to a matrix with a complex numbers. Otherwise, there is no difference in these three definitions of orthogonal, orthonormal, or a unitary matrix. Now we'll see what is a characteristic equation of a matrix. It is defined as determinant of A minus lambda I is equal to 0, where lambda is a some parameter which is called eigenvalue and I is identity matrix. So if we solve this equation by doing if you solve this equation by computing determinant of this equation, you'll get a polynomial in terms of lambda, and that can be solved to find out various roots of lambda. So typically, if it is a n by n matrix, you'll get n values of lambda, or you can say eigenvalue. Now we'll see the significance of this equation. Before that, we'll see one more equation. Whenever a matrix operates on some vector v and it results in output vector also v scaled by a factor lambda, that is a eigenvalue, then the vector v is called eigenvector. We already discussed similar concept of eigenfunction in our previous lecture of exponent function of mathematical models. If you don't have an idea of this, you can refer that lecture. Now, what is the exact meaning of this equation? So as I said, a matrix operates on a vector, which we already saw in simultaneous equation, and it generates another vector. It is a system operating on input vector v and generates output vector v scaled by factor lambda, and therefore output vector is the same as input vector, which is simply a scaled version. Such a vector is called eigenvector. Now, how to find eigenvector? So here, if you take a previous equation of a matrix which is called characteristic equation and multiplied with v on both sides, you'll get the another equation which can be used to solve value of vectors v. Now every eigenvalue you'll get a one vector. So if there are n eigenvalues, you'll get n eigenvectors, and if you stack these n eigenvectors in a horizontal fashion, then you'll get a eigenvector matrix, which is also known as a principal component analysis of a matrix A. And the important property of this matrix is it is unitary matrix if it is a complex value, or it is a orthogonal or orthonormal matrix if it is a real value. And this gives huge amount of solutions to solve many engineering problems. So one should know what is a eigenvalue, eigenvectors, and their application in real life scenario. So this concept of eigenvalue and eigenvectors is used in eigenvalue decomposition of a matrix A, because once you decompose a matrix A in orthogonal matrices or diagonal matrices, the inverse computation becomes trivial. Now in eigenvalue decomposition, if matrix A is a square matrix, then it can be decomposed into two matrices, U, which is a unitary matrix, and diagonal matrix D. U transpose is a simply obtained from U by exchanging row and columns. Now how to find inverse of a diagonal matrix? It is a trivial process. In diagonal matrix, only diagonal elements are non-zero, while rest of the elements are zero, and therefore by simply taking reciprocal of diagonal elements, one can find out inverse of a diagonal matrix. Now inverse of U, which is an orthogonal matrix or a unitary matrix, is computed by taking conjugate transpose, and therefore if you see this entire equation for A as an eigenvalue decomposition, the computation of A inverse becomes trivial. If A is not a square matrix, then there is another decomposition technique which is called singular value decomposition, where A is decomposed into three matrices, where U and V are two unitary matrices while D is a diagonal matrix. Now if A is a n cross m matrix, then the dimension of U is n cross n, dimension of V is m cross m, while the dimension of D is n cross n. So when you apply the rule of multiplication, and if you'll see the final matrix, it will match the dimension of A. Now what are the various other important properties one should learn to gain expertise in linear algebra and then apply in real life scenarios or application are rank, dimensions, basis of matrices, norm of a matrix, condition number of a matrix, positive definite, semi-definite properties of the matrices, quadratic form of a matrices, which is used in the optimization theory, principal component analysis, independent component analysis, canonical component analysis, which are used a lot in image processing subject of, that is a specialized branch of signal processing. Now we'll see simple application of a matrix, which is called a rotation matrix, very commonly used in geometric transformation and subject like computer vision. Now here consider the Euclidean plane with the point P1 at coordinates x1 and y1 with a radius r and angle phi with respect to x-axis. Now if this point is moved or rotated to another point with the same radius, say P2, with a position at x2 and y2 with a radius r and incremental angle theta, then how can you represent this system in a matrix form? So it is very simple and straightforward operation. Now consider point P2 with a radius r, then projection of x2 is given by r cos theta plus phi, because the total angle is theta plus phi. Similarly, y2 is equal to r sine theta plus phi. So if you solve this equation using trigonometric identity, you can expand it to x2 equal to r cos theta cos phi minus r sine theta into sine phi. So here you will find r cos phi and r sine phi forms x1 and y1 projections, and when you substitute, you will get a very elegant equation: x2 is equal to x1 cos theta minus y1 sine theta. Similarly, you can obtain for y2, which is x1 sine theta plus y1 cos theta. Now it looks like a simultaneous equation and can be represented in a matrix form. Now here, this parameter matrix, which is expressed in terms of sine and cos theta, operates on an input point represented as a vector with two components x1 and y1, transforms to point P2 having coordinates x2 and y2, and hence it is called a rotation matrix, and it plays a very important role in geometric transformation and orthogonal representation of the matrices, analysis of camera systems, and triangulation process. So here we'll see one more important property, which is a DFT matrix commonly used in many applications of signal processing, computer vision, and artificial intelligence. Basically, Fourier transform is a transformation of a time domain function into frequency domain. Now, DFT is applied to the discrete time signal x of n, and when one compute Fourier transform using this formula, generates frequency domain representation of x of n as x of k. Now here right now the equation is not important, but one can see the summation n is varying from 0 to n minus 1 for n, and if it is expanded for n values of k which are varying from 0 to n minus as well, then you will get n simultaneous equation, and hence one can represent in a matrix form. Now here x of n is a 1D vector, x of k is also a 1D vector, which is a frequency domain representation of x of n, and x of n is multiplied by a kernel function, which is a complex exponent function, which we already discussed in exponent function lecture, where the argument is minus j 2 pi kn by n. So minus j 2 pi by n is a constant, and we can replace it by another symbol called w. Then the kernel can be written as w raised to kn. Now here there are two variables k and n, where both k and n varies from 0 to n minus form, and hence it forms a matrix which possesses very important property called unitary matrix. So there is no need to think about how to calculate the inverse, because we already studied the rule. For unitary matrix, inverse is given by the conjugate transpose. So here the equation for Fourier transform can be written in a matrix form as capital X is equal to capital W into X, where W is a DFT matrix. So if you want to switch from frequency domain to time domain, that is capital X is given, which is a frequency domain representation, then time domain representation can be computed by computing inverse of DFT matrix. And since it is a unitary matrix, inverse is equal to conjugate transpose. So these are the very simple and beautiful applications of matrix, and this lecture also gives some fundamental idea along with the notion of a matrix. Now there are tremendous applications of matrices, such as a least square solution in case of estimation theory. There is a new subject altogether evolved, which is called optimization theory, completely based on the concepts of linear algebra. And it is a very, very important subject in most of the engineering fields. Third one is the machine learning and deep learning, where optimization theory also becomes integral part of the subject. Another important subject is a computer vision, which typically handles various camera systems. Signal processing, which is a foundation course for computer vision, machine learning, which has different types of signal processing for audio, images, and video. That is a 1D, 2D, and 3D signals, and that can be nicely analyzed, and the systems can be designed using concept of linear algebra. Statistical signal processing, which involves random processes and random variables, and it also needs help from linear algebra. Data visualization and state space representation. State space representation is used in the designing of Kalman filter, where the complete system is represented in the form of a matrix, and Kalman filter is used in tracking system, and that can be used in the object tracking in most of the artificial intelligence system. I hope you must have enjoyed this lecture, and thank you for your patience and watching my lecture.